to deep problem number 1. So did anybody spend any time over break thinking about this? Cool. Okay, so question number 1 was, what's the easiest hardware implementation of a chess playing machine? Did you get any ideas?
My only idea was to build a collection of cells which within it contain the knowledge of what that piece was. So it's a physical mapping of the chessboard.
Okay. And
then there will be a controller circuit which determines which piece would move.
Okay.
Randomly selects a piece. The piece looks ahead at using the knowledge of where it can move. It looks ahead and see if there's anything in that spot. If it's friendly or enemy, and it moves there. If it can't, it returns a signal to the controller circuit, which tells it to pick another.
Okay.
And then the 2 controller circuits on the other side would either speak or communicate somehow to know who's starting.
Okay, cool. So physically map a chessboard onto a set of cells and have information about how pieces can move, and then some control circuits to apply some kind of strategy or logic. Okay, that would be cool. Any other ideas?
So what was the question again?
What's the simplest hardware implementation of a chess playing machine? And it doesn't have to be on a cell matrix.
Chopsticks.
Chopsticks?
It's a machine, and you have to use it to play chess.
Okay, so chopsticks plus a person.
That's my smart aleck.
Okay, that works.
It doesn't have to be on a cell matrix. It could just be a giant truth table.
Okay.
And that's really simple. The only problem is getting the values for the truth table.
Okay. That's the answer I wanted. So, chessboard. Okay, you have a bunch of pieces out here. Ignoring any questions of strategy or anything like that, basically you take turns. Does everybody here know how to play chess? Basically you take turns moving pieces, and there's different rules that control where pieces can go, and you try to capture pieces and eventually try to capture the other person's king. So you can take this chessboard and you can number these squares. You can number these squares, 64 squares, so that's actually a 6-bit number to code one position on this board. And anytime you want to capture a move, you need to know 2 things. You need to know the starting position of a piece, and you need to know the ending position of a piece. And if you record that a piece was sitting here, and it moved like this, you record those 2 positions, you've got all the information about that move. So, starting position is 6 bits, ending position is 6 bits. Basically 12 bits will let you encode a move during a game of chess. So how many possible first moves are there? Disregard what's legal. What's the largest number of possible first moves? 32
pieces. There's only like 10 legal moves.
Well, disregarding legal. Yeah, there's 32, and they can move different places. An absolute maximum number would be however many options you have for a 12-bit number. Okay, so 2 to the 12, 4096. Okay, in fact, there's a lot fewer. But if you just randomly wanted to move one piece to another position, pick up this piece and move it down here, that's one move. But each of these moves can be coded with a single 12-bit number, and each 12-bit number corresponds to exactly one move. So maximum number of 4096. And in response to your opponent's first move, we're going to let them go first, you're going to make exactly one move yourself. And you have the same number of options, 4,096. So basically taking a 12-bit number and you produce a 12-bit output. And that will tell you what your first move is. And we're assuming that you're some kind of grandmaster and you know exactly what the best move is to make for each possible opening move. And so that's a function f1 of x. And then your opponent's going to make a second move, and that's going to be another 12-bit number. And your second move is going to depend on the first two moves this person made. So your second move is going to be y equals some other function of x, where in this case x is a 24-bit number, and your move is still 12 bits. Okay, in your third move, you're going to take in a 36-bit number, which shows you what the first three moves they made, and you're going to produce a 12-bit output, which is your move, and so on. And so you need a series of these functions, f of I, depending on how long your game lasts. But in fact, each of those functions has a disjoint domain. It operates on a set of numbers different from any other function. Because the input here, your first 12 bits, your first 12 bits will be non-zero, and all the other bits will be 0. Okay, down here, for your second move, there'll be something non-zero in here, and there'll be something non-zero in here, but all your other bits will be 0. And so on and so forth. And so F2 never operates on the same data as F1, which never operates on the same data as F3, and so on. And these are all disjoint. So in fact, you can combine these into a single function again, y equals f of x. So that's your simplest equation for playing chess. You basically take the coded set of inputs that have been made up to this point in the game, turn them into a big long string of ones and zeros, feed it into f, and you'll find out what your next move is. Okay, and this is basically a lookup table, or a truth table, as you said. It's like a memory in a cell, but it's much bigger. 12 times however many moves, that's the number of bits you need in your input, so absolutely massive address space. But in terms of hardware implementation, it's very simple. How do you store a lookup table somewhere? Well, in a cell, we just used a static memory, but in fact, this function f is fixed once and for all. It never has to change. So all you really need is a ROM, just a read-only memory. Okay, and that's actually that's all you need to build a chess playing machine. It's a really, really, really big ROM. Okay, now it's not practical, but in fact it's sufficient. So lookup tables. Lookup tables are everywhere. Okay, if you have a piece of paper in front of you, it's got words on it. That's really just a lookup table. You can basically say how many letters do you want to go into this page, what's the letter at that position. Okay, if you have a book, you can do the same thing. You can take a page number, you can say how many characters do you move in to that page, and what's the letter stored there. If you have a library, you start with a Dewey Decimal number of a book, and then a page number and a position on the page, and you get a letter. All this stuff is just lookup tables. And everything we do on a computer, all these programs that we write, the languages, we have objects, we have operating systems to support it, they're all just complex ways of creating lookup tables. We don't know how to write a lookup table that will play chess, for example. or solve an equation for us. But we have these indirect methods that we can coerce these machines into basically performing this y equals f of x. But we can't just code it up as a truth table. We can't just store it as for all these inputs, here are the outputs. We have to use this very indirect approach. Okay, so that brings us to deep problem number 2. This wasn't really so deep, but it's related. So in the language C, what's the one operation that most closely corresponds to the entire D-mode behavior of a cell matrix?
Switch case.
Switch case, okay. Why is that?
You do a switch on a 4-bit number and have 16 case statements.
Okay.
Or if else would, or if else.
Okay, case statement or switch statement. We can feed in what the inputs are to a cell, choose what the outputs are in each case. And this is basically another form of a lookup table, right? It's saying what the different truth values are and for each option. Okay, inside a matrix, this cell. And we're in D mode, so all of our inputs are Ds, all our outputs are Ds. This thing has a memory inside. It gets 1 bit from each of its neighbors, and it uses those 4 bits to form an address. Okay, that's the address, tells you which row in the truth table you want to look at. In using those, it selects some position inside this memory, some row of bits, and then it takes those bits and farms them out to the neighbors. One of those bits will go over to this neighbor, and it will also get bits from its neighbors, and it'll do the same thing. It'll pick some row in here, and it'll farm outputs to its neighbors, and so on. So the main thing that's happening inside each of these cells is basically pointer dereferencing. We're basically doing something like asterisk X. We're saying here's a number, but let's treat it like an address and see what's stored at that address. And we take what's stored at this address, and we take 1 bit of it and send it into a neighbor. And this cell is doing the same thing and sending a bit to a neighbor, and so on. And then this cell is taking those 4 bits, turning it into address, doing a dereferencing. Okay, so at some level, this one operation, indirection, looking at what's stored at a memory location, is essentially what's happening inside each of these. And it's a bit of a code duality, a code-data duality kind of flip. You can treat this thing as a number, or you can treat it as an address. And the operation, when you're treating it as an address or as code, is to say what's stored at that location. We're going to talk about duality in a week or 2. Okay, deeper question number 3. So you're on a desert island and you have a flatbed scanner. You have all the things that Gilligan and friends had. And you have a computer, but for some reason it won't compute scientific functions like sines and logarithms. Okay, how do you use a flatbed scanner to compute sines? I was going to bring a scanner in, but I didn't have a chance to get them together. So you know what a flatbed scanner is, right? It's something something about this big, it has a lid. You put some